In this video, I will tell you about the very important topic of module 3, which is always repeated, that is uniqueness theorem. In uniqueness theorem, we'll find out a solution, okay, telling that the solution is unique. What it states is any solution of Laplace equation that satisfies the boundary conditions must be the only solution regardless of the method used. So that the solution should be unique. That is what the uniqueness theorem tells. So we'll go with the proof by assuming that there are two solutions. Okay, there are two solutions of Laplace equation, that is v1 and v2. We assume it. So where both are general functions of the coordinates. So according to Laplace, del square v1 is equal to 0 and del square v2 is equal to 0. Equate both the solutions, that is del square v1 is equal to del square v2. Call it as equation 1. Then bring it to the LHS and take del square common. So we'll get del square of v1 minus v2 is equal to 0. Call it as equation 3. If each of the solutions satisfies the boundary conditions and potential at the boundary, we'll take the potential at the boundary as v1b and v2b, which are identical, that is v1b is equal to v2b. Bring it to the and equate it to 0 because potential at the boundary is 0. So v1b minus v2b is equal to 0. Call it as equation 4. Just keep this equation 3 and equation 4, where one equation is del square of v1 minus v2 is equal to 0. Second one is after applying the boundary condition, taking the potential at the boundary, we write v1b minus v2b is equal to 0. So these 3 and 4 equations are important, which will be substituted later. Next, how they'll go with the next is by taking a vector identity. It is important in EFT, like they'll be taking some vector identities to prove the theorem. Here what is the identity they have taken is del of V into D. Okay, del of V into D. V is potential and D is electric flux density. That is equal to, just split it. First they will write V into del of D plus D into del of V. First V is taken outside, next D is taken outside. Okay, that is equation 5. That is important. You have to remember this vector identity. Next, what I will do, take V as a scalar quantity. So wherever V is there, just substitute the difference in the potential, that is V1 minus V2. Next, wherever D is there, where D is taken as vector quantity, there you will write divergence of V1 minus V2. That is D is equal to del of V1 minus V2. Okay, so remember wherever V is there in equation 5, substitute as V1 minus V2, and in place of D substitute del of V1 minus V2. Just keep on seeing this equation 5. So at first we have del of V. Okay, instead of V what we wrote, V1 minus V2. Next we have D. In place of D what you should write, del of V1 minus V2 is equal to, in place of V again V1 minus V2 plus, in place of D one del is already there. Okay, that del and one more in this equation. So we'll get two dels there, del dot del of V1 minus V2. So keep on substituting like that. Next you have to integrate that equation for the entire volume. Just put since there are three parts in this equation, one is LHS and one is in RHS, we have two plus, using plus we have two equations. So just write integration volume, integration completely, three volumes, three integrations you do for this. Okay, del of volume, integration volume, del of V1 minus V2, del of V1 minus V2 with respect to dV. Like that you write for both LHS and RHS. Call it as equation 6. Next, apply the divergence theorem. So what the divergence theorem tells? We are equating here volume to differential surface. Just concentrate here. Integration del dot d dv is equal to integration d dot ds. Okay, differential volume is equated to differential surface. See, when we compare this divergence equation with equation 6, we'll observe that, see, it is del of, in equation 6 what we wrote, del of v1 minus v2, del of v1 minus v2 dv. So here del of D means what? Now D represents here, D is nothing but V1 minus V2 del of V1 minus V2. Okay, when we compare our divergence theorem with equation 6 LHS, so we'll get D as V1 minus V2 del of V1 minus V2. So wherever D is there, we can write like that. So differential surface equation, what will happen? What is the differential surface equation? D dot ds. So in place of D, what you can write now? Place of D, we can substitute V1 minus V2 del of V1 minus V2 ds. Okay, the LHS of a differential volume is taken and it is substituted in terms of differential surface, where the D, capital D, is written in terms of V1 minus V2 del of V1 minus V2. Next, the RHS is written same like that only. However, equation 6 RHS is written as it is, but only the LHS is changed, where the differential volume is equated to differential surface. That is the next equation. Next, what we have to do? Applying boundary conditions for the above equation. Just apply the boundary conditions. That means whatever that equation 3 and 4 we got now at the beginning, that is applied here, and some equations are equated to 0. We told that V1b minus V2b is 0. So that the first equation, that differential surface, after applying the boundary conditions, see, boundary conditions is applied only for the differential surface, not for the volume. Okay, wherever dv is there, you should not apply. Only for surface you should apply. So it will be V1b minus V2b del of V1b minus V2b ds is equal to the RHS. So the first, the LHS, that first will become 0 because of equation 4, and the second part in the volume, we had written a del square of V1 minus V2 is 0. So we have their del square. So del square of V1 minus V2 also will become 0. So the two parts will get the LHS side and the RHS first part will become 0. Therefore, the quantity under integral is 0. So the left out is integration volume del of V1 minus V2 into del of V1 minus V2. It will be like del of V1 minus V2 whole square. Okay, whole square, that is equated to 0. Since the gradient of the potential vector is 0 everywhere, so it can be written as del of V1 minus V2 is equal to 0. It is nothing but V1 minus V2 is represented to a constant, where V1 is equal to V2. So everywhere this V1 is equal to V2 or is it equal to a constant everywhere, showing that V1 and V2 cannot be different solutions of the same problem. First we went on with assuming that V1 and V2 are two different solutions, and we came to the point that V1 is equal to V2. So if a solution to Laplace equation can be found that satisfies the boundary conditions, then the solution is always unique. Okay, we'll have only the same solution in whatever method if you follow. Whatever method you have followed, but the solution will be unique. This is what the uniqueness theorem states. Okay, so we'll start with the Laplace equations with equation 3 and 4. Okay, next we'll write the boundary conditions. Next we'll use this vector identity, that is important. After using vector identity, you'll use a divergence theorem, where the volume is equated to surface instead of D. Okay, del dot D, the D is substituted, and then the boundary conditions are applied. It is equated to 0. At last we'll get V1 is equal to V2. Thank you.